For most of human history, the night sky has been a mirror. We looked up and saw our fears reflected back at us, our loneliness, our smallness. Every generation asked the same quiet question in different languages, carved into stone, whispered in prayer, written into equations. Are we alone? And if we are not, how close has life come to touching us across the darkness of space? Tonight, that ancient question has been dragged out of philosophy and placed under a microscope. Because somewhere far beyond the reach of any spacecraft ever built, orbiting a star that was already ancient before Earth formed its first oceans, there is a planet that has forced scientists to stop using words like possible and maybe, and begin speaking in numbers, precise numbers, uncomfortable numbers, numbers that suggest the universe may no longer be indifferent to us. 99.7%. That is not a guess, it is not poetry. It is a probability derived from spectra, atmospheric chemistry, stellar physics, and models refined over decades. A probability that has emerged from data collected by the most powerful space telescope humanity has ever built. A telescope designed not to inspire wonder, but to eliminate uncertainty. The James Webb Space Telescope was never meant to answer the question of life directly. It was built to see clearly, to see truth, stripped of myth and imagination. But sometimes clarity itself becomes terrifying, because when you remove the blur, when you peel back the noise of distance and time, you may discover that the universe has been signaling to us all along, patiently, waiting for us to finally learn how to listen. This is not a story about aliens landing on Earth. It is not about flying saucers or secret messages. It is about molecules, about light stretched thin by billions of years of travel, about the physics of atmospheres and the chemistry of survival. It is about a planet that should not look the way it does, a planet that, according to everything we understand about how worlds behave, is doing something extraordinarily suspicious. And if the data is right, then the universe has crossed a threshold, because the moment life is no longer hypothetical, the moment it becomes statistically likely, humanity's position in the cosmos changes forever. This is the story of how we reached that moment. How a telescope parked 1,000,000 miles from Earth began reading the fingerprints of distant worlds, and how one particular planet forced scientists to confront a possibility so profound that it threatens to redefine what it means to be human. If you value calm, intelligent explorations of the universe and the science behind it, subscribe to The Boring Universe. Like this video if you enjoy deep, thoughtful documentaries, and leave a comment telling us which part of the country you're watching from. The James Webb Space Telescope did not begin as a dream of finding life. It began as an admission of failure, a quiet recognition that humanity had reached the limits of what it could see with the tools it already possessed. By the late 20th century, astronomers had cataloged the universe with remarkable success. They had mapped galaxies, measured cosmic expansion, and detected planets orbiting other stars. But every breakthrough carried with it a growing frustration. The most interesting questions remain just beyond reach. What are the atmospheres of distant planets made of? How did the first galaxies form? What happens inside stellar nurseries buried in cosmic dust? And most tantalizing of all, are there other worlds like ours, not just in size but in chemistry and habitability? The Hubble Space Telescope transformed astronomy, but it was ultimately a creature of visible light. It could show beauty, structure, and motion, but it could not see through dust, nor could it read the subtle chemical signatures that determine whether a planet is dead or alive. For that, astronomers needed infrared vision, extreme sensitivity, and stability so precise it bordered on obsession. James Webb was conceived as a machine of patience, a telescope that would not simply take pictures but collect whispers. Every photon it captures is ancient, fragile, and irreplaceable. Lose one, and it is gone forever. To detect life across interstellar distances, Webb would need to measure changes in light so small that they approach the limits of physical possibility. Unlike Hubble, James Webb does not orbit Earth. It resides at the second Lagrange point, a gravitational balance nearly 1,000,000 miles away. There, shielded from Earth's heat and interference, Webb exists in a perpetual night. Its massive sunshield, the size of a tennis court, blocks sunlight, moonlight, and Earthlight simultaneously. On the cold side of that shield, instruments are cooled to temperatures colder than deep space itself. This is not engineering excess. It is necessity. Infrared astronomy demands silence. Thermal noise can drown out the faint signals of distant planets. To detect the atmosphere of a world dozens or hundreds of light years away, Webb must operate in an environment so stable that even microscopic vibrations are unacceptable. The telescope's primary mirror, composed of 18 hexagonal segments coated in gold, is not smooth in the everyday sense. It is smooth to within fractions of a wavelength of light. This precision allows Webb to act not as a camera, but as a spectrograph. It breaks starlight apart, separating it into its component colors, revealing absorption lines that correspond to specific molecules. This is how planets betray themselves. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching the telescope. Molecules in that atmosphere absorb specific wavelengths, leaving dark fingerprints in the spectrum. Water vapor, carbon dioxide, methane, oxygen, ozone, ammonia. Each leaves a distinct signature. Each tells a story about temperature, pressure, chemistry, and potential biology. Before Webb, these signals were largely inaccessible. The noise overwhelmed the data. Models were speculative, constrained by guesswork. Webb changed that. It did not merely improve resolution. It crossed a threshold where atmospheres could be measured, not inferred. This ability reshaped exoplanet science almost overnight. Instead of asking whether planets existed, astronomers began asking what kind of planets they were. Rocky or gaseous, hot or temperate, chemically sterile or intriguingly complex. But complexity alone does not imply life. Planets can host exotic atmospheres shaped entirely by geology and radiation. Venus is a cautionary tale. Similar in size to Earth, yet hostile beyond imagination. A reminder that habitability is fragile, contingent, and rare. To assess life, scientists look for disequilibrium, chemical imbalances that should not persist without continuous replenishment. On Earth, oxygen exists because life constantly produces it. Methane coexists with oxygen only because biology keeps both from annihilating each other chemically. Remove life, and these gases disappear on geological timescales. This insight forms the backbone of modern astrobiology. Life is not detected directly, but through its consequences, through the scars it leaves on planetary chemistry. As James Webb began surveying exoplanets, scientists expected surprises. What they did not expect was consistency. Over and over, Webb found atmospheres that made sense, hydrogen-rich envelopes. Carbon dioxide dominated skies, steam worlds too hot for liquid water. The universe behaved predictably, until it didn't. The planet at the center of this story was not the largest, the closest, or the most famous. It did not orbit a sun-like star in a perfectly Earth-like orbit. At first glance, it was merely interesting, a candidate among many. But as data accumulated, subtle anomalies emerged. The star it orbits is a red dwarf, smaller and cooler than the Sun. Such stars are common, comprising the majority of stars in the Milky Way. Planets around red dwarfs often face extreme conditions: tidal locking, intense stellar flares, atmospheric erosion. Historically, these environments were considered hostile to life as we know it. Yet this planet resides in the star's habitable zone, where temperatures could allow liquid water on the surface. That alone was not remarkable. Thousands of such candidates exist. What was remarkable was the atmosphere. Initial spectra revealed water vapor, not in trace amounts but abundantly. Carbon dioxide appeared as expected, but then came methane, present at levels difficult to explain through known non-biological processes alone. Further observations hinted at additional compounds, potentially including dimethyl sulfide, a molecule on Earth produced almost exclusively by living organisms. At this stage, caution dominated. Astrobiology has been humbled before. Abiotic pathways can surprise us. Models were tested, retested, and stress-tested. Could volcanic activity produce these signatures? Could photochemistry mimic biology? Could stellar radiation sculpt an atmosphere into this configuration? Each alternative explanation strained plausibility. As more transits were observed, uncertainty shrank. Error bars tightened. Statistical confidence increased. Eventually, researchers began using language they rarely allow themselves. Not confirmation, but likelihood. Not proof, but probability. 99.7% does not mean life has been found. It means that given current models, known physics, and observed data, the atmospheric composition is overwhelmingly consistent with biological activity rather than purely abiotic processes. This distinction matters. Science does not declare life lightly, but it does quantify uncertainty. And when uncertainty collapses, implications expand. This planet does not scream life, it whispers it. And whispers are harder to dismiss. The implications extend beyond astrobiology. If life can arise and persist around red dwarfs, the most common stars in the galaxy, then life may not be rare at all. It may be abundant, quietly thriving on worlds we have barely begun to notice. James Webb was built to answer questions about the early universe, about star formation, about cosmic structure. In doing so, it may have answered something far more personal, that life is not a cosmic accident limited to one fragile blue world, but a process woven into the fabric of planetary evolution itself. Life, when viewed from the inside, feels obvious. It breathes, grows, adapts, and persists. But from across the vast distances of space, life becomes something far stranger. It is not a creature or a shape or an intelligence. It is a pattern, a sustained defiance of equilibrium, a planetary scale imbalance that should not exist unless something is actively maintaining it. This is the central challenge of astrobiology, not how to imagine life, but how to recognize it when it does not announce itself. On Earth, life rewrote the planet. Before biology took hold, Earth's atmosphere looked nothing like it does today. Early Earth was dominated by carbon dioxide, nitrogen, and trace gases shaped by volcanism and impacts. Oxygen, now the most conspicuous sign of life, was almost entirely absent. When photosynthetic organisms began releasing oxygen as a waste product, it accumulated slowly at first, then catastrophically, triggering the Great Oxidation Event. This was not subtle. It altered the chemistry of oceans, the color of rocks, and the evolutionary trajectory of every organism that followed. From space, Earth's transformation would have been unmistakable, a planet glowing with chemical tension, oxygen coexisting with methane, water vapor cycling through clouds and oceans, a surface temperature regulated not merely by distance from the sun, but by feedback loops involving life itself. This is what scientists search for now, not cities or signals, but chemical stories that do not add up without biology. The planet identified by James Webb presents such a story. Its atmosphere does not rest quietly in chemical balance. Instead, it appears to be caught in a state of perpetual disruption. Gases that should destroy one another persist together. Molecules that should be fleeting appear stable. Energy flows in ways that suggest regulation rather than chaos. Understanding why this matters requires understanding how planets behave when life is absent. A lifeless planet trends towards simplicity. Over time, chemical reactions proceed until they exhaust available energy gradients. Reactive gases combine, settle, and stabilize. Volcanism may introduce temporary complexity, but without continuous replenishment, atmospheres eventually calm. Mars is a case study. Once warmer and wetter, now thin, cold, and chemically quiet. Venus, too, despite its violence, is chemically monotonous, its atmosphere locked into a stable but deadly configuration. Life interrupts this process. It exploits energy gradients and in doing so creates new ones. It accelerates some reactions and suppresses others. It builds complexity and refuses to let it decay. From a thermodynamic perspective, life is an organized rebellion against entropy, sustained only by constant energy input. The signatures James Webb detected align with this kind of rebellion. Water vapor alone is not enough. Water exists on many worlds. Carbon dioxide is common. Methane can arise through geological processes. Even oxygen can be produced abiotically under certain conditions. But the simultaneous presence of multiple reactive gases, maintained at levels inconsistent with known non-biological mechanisms, changes the equation. This is where probability enters. Scientists do not claim certainty because certainty requires direct sampling. What they claim is that given everything we know about planetary physics and chemistry, life becomes the most parsimonious explanation. This does not mean the life is complex. It does not imply intelligence or even multicellularity. On Earth, for most of its history, life consisted entirely of microbes. Single-celled organisms dominated for billions of years, shaping the planet long before animals emerged. If life exists on this distant world, it may resemble Earth's earliest biosphere far more than its current one. And yet, even microbial life is revolutionary. The presence of life anywhere beyond Earth immediately transforms biology from a local phenomenon into a cosmic one. It implies that life arises readily when conditions allow, that chemistry naturally organizes into self-replicating systems, that the universe is not sterile by default. But caution is essential. History is littered with premature declarations. In the 20th century, astronomers believed canals existed on Mars. Meteorites were claimed to contain fossils that later proved ambiguous. Even now, methane on Mars continues to spark debate rather than consensus. The difference this time lies in data quality and statistical rigor. James Webb does not offer a single ambiguous measurement. It offers repeated, independent observations across multiple instruments. Each pass of the planet across its star adds clarity, reducing uncertainty. Models that exclude life struggle to reproduce the observed spectra without invoking extreme, finely tuned conditions. Exotic chemistry, improbable geological rates, or unknown processes must be stacked together to avoid a biological explanation. This does not make them impossible, but it makes them increasingly implausible. Science favors the explanation that requires the fewest unsupported assumptions. At present, biology appears to be that explanation. Still, the term 99.7% demands respect. It is not a proclamation. It is a confidence interval. It acknowledges that unknown unknowns remain, that nature may yet surprise us. That humility is not optional when confronting the cosmos. What makes this discovery especially compelling is not just the chemistry, but the environment. Red dwarf stars were long considered unlikely hosts for life. Their habitable zones are close in, exposing planets to stellar flares and radiation. Many such planets become tidally locked, with one side perpetually facing the star and the other locked in darkness. But recent research has complicated this picture. Atmospheric circulation models show that thick atmospheres and oceans can redistribute heat effectively, preventing atmospheric collapse. Magnetic fields may shield surfaces from radiation. Water clouds on the day side may reflect stellar energy, stabilizing climate. In other words, planets once dismissed as hostile may in fact be resilient. If life has found a way to persist under such conditions, it suggests that habitability is broader than previously imagined. The classical habitable zone, defined by distance alone, may be only a rough guideline. Life may thrive in niches shaped by atmospheric dynamics, geology, and chemistry rather than simple orbital geometry. James Webb's role in revealing this cannot be overstated. By shifting exoplanet science from detection to characterization, it has forced a reevaluation of assumptions that guided the field for decades. But there is a deeper implication still. Life, if it exists on this planet, is not hidden beneath ice or buried underground. It is interacting with the atmosphere. It is shaping the planet in a way that can be seen across space. That implies longevity, stability, time. Life that persists long enough to alter an atmosphere must survive millions, perhaps billions, of years. It must endure stellar variability, impacts, and climatic shifts. It must integrate itself into planetary systems so deeply that its absence would leave a scar. This is not fragile life clinging to the edge of extinction. It is life that has learned how to belong. Such persistence raises profound questions about convergence. Did life there follow a path similar to Earth's, or did it invent entirely different solutions to survival? Are there universal strategies that life converges upon, or is biology endlessly inventive? We cannot yet know, but the chemistry offers hints. Certain molecules are efficient carriers of energy and information. Carbon-based chemistry is versatile and robust. Water is an exceptional solvent. These facts are not Earth-centric biases, they are consequences of physics. If life elsewhere uses similar chemistry, it suggests that biology is constrained by universal principles, that the universe nudges life towards certain forms not by coincidence, but by necessity. This perspective reframes the search for life as a search for inevitability rather than rarity. The planet James Webb has revealed may be one data point, but data points accumulate. Already other worlds show intriguing signs. Atmospheric water here, carbon chemistry there, a growing catalog of complexity. What makes this case exceptional is not isolation, but clarity. Still, restraint defines responsible science. Researchers emphasize that follow-up observations are required. Additional wavelengths must be studied. Seasonal variations monitored, alternative models refined. Science advances not by declarations but by attrition, by slowly eliminating doubt until only one explanation remains standing. If that explanation turns out to be life, then humanity will have crossed an invisible line. The question of whether life exists elsewhere will be replaced by questions of how common it is, how it evolves, and whether it ever becomes aware. For now, the significance lies in perception. We are no longer searching blindly. We are measuring, calculating, and constraining possibilities. We are learning how to read planets as systems rather than points of light. James Webb has not shown us aliens. It has shown us something more unsettling. That life may not announce itself with spectacle, but with balance, with persistence, with quiet chemical signatures that speak across space. And in doing so, it has forced us to confront a humbling possibility, that Earth is not unique in its aliveness, but merely one expression of a cosmic tendency toward complexity. As we move forward, the challenge will not be finding wonder, but integrating it. accepting that life may be a natural outcome of planetary evolution, not a miracle reserved for one world. There is a subtle but irreversible shift that occurs when a question stops being philosophical and becomes scientific. For centuries, the idea of life beyond Earth belonged to speculation, theology, and imagination. It shaped myths and inspired fiction, but it did not constrain reality. Now it does. Probability has weight. Evidence is momentum. A planet with a 99.7% likelihood of life does not announce a discovery. It establishes a context. From this point forward, every discussion of biology, evolution, and humanity's place in the universe must account for the possibility that life is not exceptional but expected. This realization does not diminish Earth. It reframes it. Our planet becomes a case study rather than an anomaly, a familiar example of a process that may be unfolding quietly across the galaxy, wherever conditions allow chemistry enough time and stability to organize itself. The silence of the universe, once interpreted as emptiness, begins to feel provisional. Not evidence of absence, but of distance, of timescales that dwarf civilizations, of signals that are subtle rather than loud. Life does not need to broadcast to exist, it only needs to persist. James Webb has not answered whether we are alone. It has done something more profound. It has made solitude unlikely. And in that quiet adjustment of expectation, humanity steps into a new era, one where the universe is no longer a backdrop to our story, but a participant in it.